Chapter 4 is all about integration. We're integrating functions. What's integration? Well, to put it bluntly, it's the opposite of differentiation. We've been taking all these derivatives. Well, now we're trying to learn how to untake all these derivatives. So antiderivative of an algebraic function. How do I work backwards from a function, or from the derivative to the original function? That's what we're working on. And we're going to recognize why we need this thing that we call a constant of integration. We'll get to that in a minute. We'll define the definite integral and its parts. And last but not least, we're going to try to learn how to deal with trig. So we're going to deal with algebraic functions, and we're going to deal with trig functions, and we're going to learn about this thing that we're going to call an indefinite integral and what the pieces of it are. So antiderivative. So the problem that I like to do from time to time with classes is, what would I have taken the derivative of in order to get 3x squared? And people throw stuff out like, well, you could take the derivative of x cubed to get 3x squared. And some people say, well, that's the only answer. Well, wait a minute. What if it was x cubed minus 8? Well, the derivative of x cubed would definitely be 3x squared. Derivative of negative 8 would be 0, so that would work too. What about x cubed plus, I don't know, 12? So conclusion that I'm hoping that we can come to pretty quickly is there's about a billion things, that are an infinite number of things that we could take the derivative of in order to get 3x squared. What do they all have in common? They all have an x cubed associated with them, but the number that goes along with can change and can vary, and, well, which one's right? Well, the truth is none of them are right. There's many, many, many of them. So general antiderivative of f of x equals 3x squared. What happens, what does this mean? Well, when I take the derivative, you know, we're used to saying if I take the derivative of an f of x, I get f prime of x. If I take the derivative of f of x, I get f prime of x. So now I'm going the other way. Instead of taking the derivative of this f of x, I want the antiderivative of this thing. Well, the antiderivative means I'm going the opposite direction. The antiderivative of a lowercase f of x is going to be a capital f of x. That's just kind of how math people do it. Well, what did you take the derivative of in order to get 3x squared? We just said a second ago, well, it's x cubed plus a number. I don't know what that number is, so we like to throw this thing that we call a c in there. And this c, we're going to find out in a couple of seconds, is called our constant of integration. So I'll fit that in with my goals in a couple of minutes. Indefinite integral. Indefinite. Indefinite meaning there's lots of things that it could be. Indefinite integral means there's some uncertainty there when you put the word in, or the prefix in front of it. So an indefinite integral is really this indefinite, or is this antiderivative process. Well, here's what it really is. This thing down here, this is called the integral symbol. Okay, this funny looking swirly S, or whatever you call it, this is called the integral symbol. And the integral symbol can't exist without a variable that we're going to integrate with respect to. So we call this the variable of integration. And this thing in the middle, this f of x right here, let's make it a different color. This f of x that's in here, this is called your integrand. Well, what is that? Well, the integrand is what you get if you take your final answer and differentiate it. So this f of x that I have underlined in blue right here is kind of like your derivative, but you're trying to work backwards to find the original function. So the integrand is kind of the derivative that we would have gotten. And when we come over and we look at this, well, then this capital F of x, as I said, if you take the antiderivative of a lowercase f of x, as is underlined in blue, you're going to get the capital F of x plus this c. This c over here is called the constant of integration. The constant of integration. Why do I have to have it? Because there's about 1,000 things that I could put there and still have this capital F of x make sense, as I showed up here. There's 3 different choices I have in blue right there for the antiderivative of 3x squared. This constant, this green that we have, is kind of the thing that ties it together. All right, so what's this dy over dx? Where does all this come from? Well, I'm going to start this thing, and I'm going to say, you know what? I'm starting with dy over dx equals f of x. my derivative is equal to f of x. Well, now where does this line come from? Well, here's where this line comes from. I'm going to start by multiplying both sides of this thing by dx. So dy is the same thing as lowercase f of x multiplied by dx. I basically just separated my variables. Well, now I want to work backwards. I want to know what did I take the derivative of in order to get this lowercase f of x. So I'm going to bring in this integral symbol. This integral symbol. Well, wait a minute. What's between this first green integral symbol and a y and the dy? There's a 1 right there. Well, what is the antiderivative of 1 if we're taking it with respect to y? Antiderivative, what do you take the derivative of in order to get a 1? Well, you take the derivative of a y. What's the derivative of y? It's 1. Right side, what do you take the derivative of in order to get lowercase f of x? You take the derivative of capital F of x. Oh yeah, but don't forget, we don't know what number might be added to it, so we bring in that c. So this is where all this information down here on the bottom comes from. So antiderivative, integral symbol, so the integrand and the antiderivative are kind of the same thing. We're reversing the process of taking derivatives. And I understand right now if you feel like that's a little bit crazy, a little bit over our head, let's try to put this in practice a little bit. So taking a derivative. If I want to take a derivative, what do? Well, I start with the power. There's a couple steps. What am I going to do? I bring down the power, or I multiply by the power. Let's write it like I'm supposed to. We multiply by the power. And then what do? We subtract 1 from the power. Okay, that's not going to surprise anybody. We've been doing this all along. Well, what happens if I take an antiderivative? Anti would mean do the opposite. Do the opposite. So let's reverse the process. Well, what would be the opposite of what I have written in red over here on the left-hand side? Well, you'd want to do them in reverse order, and you'd want to undo each one. So if I want to take an antiderivative, we're going to start by add 1 to the power. So let's see. So what my new power be? My new power here would be x raised to the n plus 1 power. Then we'd have to undo multiplying by power, so we'd want to divide by the new power. I know I'm supposed to be using the exponent right here, but we're going to get over it. So I would want to divide by the new power. And last but not least, don't forget your constant of integration, plus my c. So what did we just do? We just undid the whole thing. We just said, what would I normally have done? Take a derivative, and I would have done in red. I would have multiplied by the power and subtracted to create a new one. Here, we're going to add 1 to the power to create the new one. We're going to divide by that new power, and then we're going to remember that constant of integration. So let's try this. Let's try this with this problem number 1. So this problem number 1, here we are. So I've got 3x. First thing I notice is this 3 would be a number. So this is really the same thing. That 3 could come to the outside and be a constant, and we could really be integrating x with respect to x. So we're integrating with respect to x. The integral starts with this funny-looking swirly thing, and it ends with the variable. So we're really integrating an x, and we really have 3 times as large, whatever I might have, because there's that 3 that's out there for the constant. So let's try this. So if I add 1 to the power, this is x to the first right now. So let's add 1 to the power. If I add 1 to the power, that's going to be an x squared. If I divide by that new power, that's going to be over 2. And when I bring the 3 down, I'm going to multiply all of that by a 3. And don't forget your c. So if I do that, what I really have is I have 3/2 x squared plus my c. Oh, wait a minute, Mr. Perkins. You did this out of order, because shouldn't this 3 apply to all of this stuff? Shouldn't that 3, kind of as it comes along for the ride, shouldn't it apply to the c also? Well, we could put a 3 on that c, but 3 times a constant is still a constant, and we still don't know what it is. So what will really happen with a problem like this, is we'll take this thing and we'll rewrite it, and we'll call it 3/2 x squared plus some new constant that we'll just refer to as a c, and that thing in the pink box is the antiderivative of the quantity 3x. If you want to check it, how would you check it? Take the derivative. What's the derivative of 3/2 x squared? Well, let's see. 2 times 3/2 would be 3x to the first. What's the derivative of c? A 0. The derivative of the pink box is what's in green, which is what we started with as our integrand. Second one. Here we are again. We got this crazy term. It looks like maybe we should be undoing the quotient rule. Oh, no, we're going to have to do all kinds of crazy stuff here. Well, here's what I'm going to tell you. You need to get this thing down to single terms. Let's rewrite this integral. If we rewrite this integral, what I have going here, how about this? Let's call it the integral of x over root x plus 1 over root x dx. We'll rewrite it again. If I rewrite it again, this is really the integral of x to the 1/2 plus x to the negative 1/2 dx. Two terms, two integrals, just like when we do derivative. For each term, we're going to do a derivative. Here, for each term, we're going to do an antiderivative. So if I go to do that, let's see. So let's, first term, let's add 1 to the power, x to the 3/2. Let's divide by that new power. Divide by 3/2. Let's add c. Plus, let's do the other one. Add 1 to the power, x to the positive 1/2. Divide by that new power. Divide by 1/2. Don't forget c. There's your antiderivatives. We've done them. We're good. Now let's clean it up. Blue one. Dividing by 3/2 is the same as multiplying by 2/3. X to the 3/2. Red one. Dividing by 1/2 is the same as multiplying by 2. And what we really have is we have two c's there. Well, when we have two c's there, if you add those two constants together, it's just going to be a new constant. We still don't know what it is, but we have this new constant. And when you guys look at this, what we're going to find is when you have multiple c's like this, they're going to combine together to become one constant. So you don't have to add it to each individual term. You just have to end up adding it to what your new value will be. So constant kind of gets added on in the step where you take the antiderivative. Kind of becomes its own little animal there as you work your way through it. All right, last one. Now we got some trig. Trig, actually, you're going to look at this. You're probably not going to like it very much because you're going to freak out about trig. But I'm going to tell you, knowing what you know about trig, turn it into one of your derivatives. You've got 6 derivatives that you're supposed to know at this point. Is anybody's derivative sine x over cosine squared? No, probably not. So use your powers of identity or of verifying identities. Let's change this. What if we call this sine x over cosine x times 1 over cosine x dx? All I did is I rewrote it. Well, now if I rewrite it again, this is the integral of a tangent of x times a secant of x. Is anybody's derivative tangent of x times secant of x? Yes, of course it is. If you take the derivative of secant of x, you'll get tangent of x times secant of x. And don't forget that constant of integration. So the key with trig problems is you've got to turn it into somebody's derivative. That's somebody's derivative. Whose derivative is it? It's secant of x. Once you've got that, you are golden.